Okay, so now I'm just going to talk a little bit about the double slit stuff that we did last year. So we did do a bit of work on this. So I've just got a picture here, which is of the double slit setup. So you can see we've got a ray box, which is shining at a double slit here. And then on the screen here, we see our interference pattern. It's a bit of terminology that we need to use. We've got bright and dark fringes in this picture. So in the middle, right in between, we've got some bright fringes. And next to it, we've got dark fringes. Okay. So the thing to remember for this is it's all about the path difference that the light takes going from each of the two different slits. So if I call this slit 1 and slit 2, the path difference is the difference in the distances that the light travels from one slit than from the other slit. Okay, so if you remember, in order to get a bright fringe, we need to have constructive superposition. And that means those two waves arrive in phase. If we think about the path difference, that gives us, well, if they're in phase, it's going to be some multiple of 2 pi, the phase difference between them. But if we talk about the path difference, that's measured in fractions of a wavelength. So if we have n wavelengths, where n is an integer, then we should get a bright fringe. So looking at those bright fringes, in the centre, here, there's going to be 0 path difference. They're going to have travelled the same distance from slit 1 as from slit 2. In the next slit along, right from here, would have had to have travelled further than from here, and specifically, it will have had to have travelled lambda metres further. So we've got a path difference there of lambda. Finally, for the next bright fringe, we're going to have 2 lambda there. So it goes up by 1 lambda each time. With the dark fringes, on the other hand, we're going to have destructive interference. And so those waves are arriving in antiphase. So if we think about the phase difference when it's in antiphase, measured in terms of pi, that means they're going to be arriving half a wavelength apart. So there's one wave, there's the other wave. So these are in antiphase. They've got a phase difference of pi radians. But when we're talking about path difference, that means it needs to be a multiple of half a wavelength. So we say it's going to be n plus a half lambda is my path difference, again, when n is an integer. And then I'll get destructive superposition at that instance. So that's my double slit interference pattern. So you need to be able to describe what these terms mean, path difference, phase difference, and so on. But there's also an equation that you guys need to be able to apply. So I'm going to write that down here. The equation you're given, as it is in the IB formula booklet, is lambda capital D over D. So I'm just going to highlight what each of these terms mean. So lambda is obviously your wavelength in meters. Big D is the big distance, so that is the distance from the slit to the screen. So we call that the slit to screen distance, again measured in meters. Small d, well that one there, that is your slit separation. So that's going to be the distance between those two slits. Lastly, S here, that's what we call the fringe separation. So that's the distance from one bright fringe to the next. Okay. So in our picture here, that would be this distance here. One bright fringe to the next. If we measured across 10 or 20 bright fringes and then divided by 20, we could get a more accurate value for D there. So at the core of it, that is your double slit material that we did last year. Properties of your double slit pattern. So take a little look at the bottom here. What we've got. So this is your double slit pattern. So we can see this pattern that we've just observed. So on the x-axis, we've got the angle here. So in this instance, that would be the angle. If I draw a line on this graph so you can see, from the centre line to that point, that's going to be the angle we're talking about. So from the centre line up to where that fringe is. So we've got the angle on the x-axis, and on the y-axis we've got the relative intensity. And we can see that when we've got high relative intensity, that's going to be a bright fringe. And when it's down at 0, that's going to be a dark fringe. So we've got this alternating bands of bright and dark fringes. What we get, however, is we still get a interference pattern when we have a single slit. And that looks a bit like what we see here. So this here is our single slit interference pattern. So we can see we still get interference patterns. So we still get this bright bit in the middle. Then we get a dark fringe. We get a much dimmer bright fringe and dark fringe, and then you can't really see on here, but that does go on further. So we do still get this interference pattern with a single slit, and that's a bit weird, and that's what we're going to be exploring now. So this here, this is my single slit interference pattern. So it's got a few characteristics, and we're going to be talking a little bit about what those characteristics are in a second. So we can see we've got this big central maximum, and then the other maxima are much smaller. But we still do get this destructive interference occurring as well. What we've got at the bottom here, this is the superposition of the two. So when we look at our double slit pattern in real life, this is what we normally observe. So we call it a double slit pattern inside the single slit envelope. So this here, this is the single slit pattern, and so you can kind of imagine, if I do this in a different colour, that this line I'm drawing here is the single slit pattern, and so that double slit pattern inside that single slit envelope is what we would observe when we actually look at a double slit pattern. Okay, so we're going to explore a little bit more about this single slit interference pattern and exactly why we do get some interference. Okay, so here in the bottom picture, double slit pattern, well here, that's the double slit pattern inside the single slit envelope. So we can compare those two. We've got the alternating bright and dark fringes of our double slit pattern there. But looking beyond that, we can see that overall, we've got some local minima here, where those bright fringes are slightly darker, and another one here, and another one here. And so this is our single slit envelope we're talking about. Okay, so let's take a look at this now. So this is my single slit interference pattern. Now, it's got some main characteristics that you guys need to be aware of. So we're going to just talk about those now. So firstly, one of the most striking things is that we've got this really, really big central maximum. So very bright central maximum. So right in front of the single slit, we get a really bright bit. And that drops off quite steeply. This point here is much, much, much brighter than this point here. And in fact, It's about 20 times as bright as the next maxima, so, which is about 5% of the bright one. Okay. Also, if we take a little look at these maxima, we can see the width of that one is much wider than these two. And in fact, the width of that central maxima is twice as wide as the other maxima. So that's the second characteristic that we need to be aware of. Okay, so often in exams and things, you guys are given the axes and you're asked to draw the single slit diffraction pattern. And when I'm marking exams, what I'm looking for is that central maximum much, much, much bigger than the next maximum? And is it twice as wide? Okay. Good. So what we also have an equation that goes along with this. So my single slit equation, I'm going to give you that now. So my equation is given in your formula booklet. I will show you where that is. So in your formula booklet, if you turn to, it's all part of chapter 9.1. So this is your single slit formula here. Theta equals lambda over b. So let's explore that. Okay. So, firstly, we know that, well, lambda is going to be the wavelength of our initial source, again in meters. Now theta, what's that going to be? So if you look at this situation here, let's say this is my screen here, along that line. So, my theta in this instance will be the angle to the first minima. So it's the angle between the centre line and the first minima. So it's ever so slightly different to what we had in our double slit equation, whereas in the previous equation, we were looking at the distance between bright fringes, or in other words, between one maxima and the next. Here, this is different. This is the angle between the centre line and the first minima. So the first dark bit. Okay. B, on the other hand, that's going to be the width of that slit in meters. So that's going to be that distance there. So we've got a few bits here. So we've got this value B, the width of the slit, and then theta, the angle to the first minima. Okay, we're going to do a little derivation of that equation in a second. But firstly, I'm going to give you a minute just to think about, okay, given this equation, what will happen to my pattern as I increase the width of the single slit? So have a little think about that one now. Pause the video if you have to. So, increasing the width of my single slit. Okay, so in my equation here, the value for B, the slit width, is going to increase. So, what does that mean for my theta? Well, if B is going up, that means my value for theta will decrease. Fine. that doesn't quite answer the question then. What will happen to my interference pattern? So what will decreasing theta look like? So, question there. Theta will decrease. So how does that look? Well, that means if the angle between here and here gets smaller, well, that means that pattern is going to get closer together. So my maxima are going to get closer together. Also, if they get closer together, that means all that light is concentrated into a smaller area. So what does that mean for the appearance of the maximum fringes? Well, that means they're going to get brighter. Now, I'm just going to add something to our original single slit characteristics. Just a bit of a reminder. If we remember, intensity is proportional to the amplitude squared. This is something we did a long time ago. So let's have a think what that actually means. If I've got a wave like this, and it interferes with another wave in phase, like so. So these two waves are going to constructively interfere. So what's the resulting wave going to look like? Well, it's going to be a constructive superposition. We add the displacements at each point. And if they're in phase, that means I'm going to have an amplitude that's twice as big. So if that's A, that amplitude there will be 2A. So, how much brighter will that bright fringe look? Well, it's going to have 4 times the intensity. If we say intensity is proportional to amplitude squared, and I'm doubling my amplitude, well, that means my intensity is going to go up by a factor of 4. So it's always worth remembering that. Okay, so what I'd like to do now is just talk you through the proof behind this single slit equation. Now, it's a bit of an interesting one, so I'm going to take you through it bit by bit. Okay, so what we've got here is a zoomed-in version of our single slit pattern here. So just bringing in the theory we had with the double slit interference there, if we look along this centre line here, we can say that light from the top of the slit and light from the bottom of the slit will have travelled the same distance to get to this point here. So we're going to have 0 path difference. And so we're going to have that central maxima. We're going to get constructive superposition. And so all these bits here, that very top and that very bottom are going to constructively superpose. If I go down a bit, these 2 points will both constructively superpose. And so because of the symmetry, we're going to have constructive superposition here. Okay, so what I'd now like to focus on is this point up here. So this is our first minima. And that means that we get destructive superposition. Okay, so that means if we're getting destructive superposition, if we think back to our original criteria, well, that means we have to have a path difference of n plus a half lambda. And that first one is going to be half a wavelength apart, so lambda over 2. Okay. But path difference, well, it was kind of obvious when we were talking about the singles with the double slit, because we could say, okay, path difference from the top slit to the bottom slit, how much further did one travel than the other? Well, this is a bit different, really, because we've only got one slit now, so how can we have path difference when you've only got one slit? Well, what we need to think about is light from different points along that slit. So now, there's a theory that goes along with waves called the Huygens theory of waves. Now, Huygens was a scientist who came up with a lot of the original theories behind wave behaviour, and he came up with a principle that I'll write the principle out here. So he says every point on a wave front can be considered as an individual source of wavelets. So it doesn't mean very much as it's written, but if we think about these wave fronts here, what that means is if I take all these different points along that wave front, I can treat them as each generating their own waves similar to this point here. We can see the waves being generated by that point. Now, if I do the same thing with one of these, I'm going to get a set of circles like so. If I do the same thing with the next point along, this one, I'm going to get some concentric circles, and so on. Now, don't worry too much about this theory, it's not a big part of the IB, but why this is useful is the superposition of those will give me the resulting waveform. Now, this is quite useful for understanding what's going on with our single slit. The key point being, we can consider different points along that single slit as being individual sources. So we kind of did that already. We talked about the top and the bottom. Okay, so I'm going to need you to bear with me for this bit. So, what we've got here is a simplified version of my single slit. So I'm just going to bring it over here so we've got a bit of space. Okay, so the IB notation, I'm just going to change that, uses B for the single slit width, but you might see different letters used in different textbooks. So we are specifically looking now at the first minima. Okay, so what we've got here is both of these rays are pointing towards the first minima. So if we follow those along, they would both end up pointing at this point here. Well, take a little look at this picture. If I look at lines 3 and 4 here, we can see they're clearly not parallel, whereas these lines do appear to be parallel. Well, really, the only reason that is because, well, this drawing is not to scale. Clearly, the distance I'm talking about could be several meters, whereas my slit width is only going to be on the order of fractions of a millimetre. So, clearly that value there is much, much bigger than the width of the slit. So if we can consider that, then really these two lines can be considered to basically be parallel. Okay, so what I'm going to do now is I'm not going to look at the whole slit, I'm going to look at two different points. So specifically, I'll do these in yellow so we can see. I'm going to look at this point here, right at the top of that slit, and this point here, which is just under halfway down. So the distance between those slits, sorry, those two sources, is going to be half the total slit width. So the distance between those will be B divided by 2. So a ray from each of those going towards the first minimum, we're going to have one like that and one like that. So these rays are basically parallel. Now, let's use the conditions that we mentioned earlier. We know if it is a first minimum, that means that we have to have a path difference of one wavelength. So, how does that work? Well, if we look at these two rays, this bottom one has travelled a little bit further. That's the path difference we're talking about. That bit there in red is going to be the path difference. So using a bit of trigonometry, this theta here that we've just mentioned, that's the angle to the first minima. And using a bit of geometry, you can prove that that's the same as that one there. Okay, so now we've got a bit of trig. So let's come up with a little equation based off that. So we're going to use that value there, and that value for theta. So let's have a wee look. Okay, so my opposite is going to be lambda over 2. The hypotenuse of my triangle, if that's my right angle there, will be given by b over 2. So given an equation, SOHCAHTOA, I'm going to end up with b over 2 sine theta equals lambda over 2. So what we're going to look at, we're going to try and change that equation to this single slit equation I showed you already. Okay, so we've got a factor of a half on both sides, so we can get rid of that. They will cancel out. So we end up with b sine theta equals lambda. Now, from maths, you may have heard of something called the small angle approximation, which basically says, okay, well, if the angle is very small that we're looking at, and in this case, that's going to be the case because our slit width is much, much less than the distance to the screen, we can say that sine theta is approximately equal to theta, the angle in radians. So that's just one of these identities that you have in maths. Okay. So so you can see already, I'm sure, that's going to make this turn this equation into b theta equals lambda. So theta equals lambda divided by b. So that is our derivation of our single slit equation there. Okay. So main things to remember, you need to be able to apply this equation. You need to be able to describe the characteristics of the single slit pattern. And you need to be able to remember, I think one of the most important things to remember is that this value for theta is the angle to the first minimum, rather than between the maximum fringes that you would observe in the double slit interference pattern. Okay. Lastly, I just wanted to talk about what happens if you have more than 2 slits, or if you just keep increasing the number of slits that we're observing. So, what we have is, when we have 1 slit, so that's the single slit interference pattern we've just been talking about. 2 slits, we've mentioned already, that's the double slit interference pattern inside the single slit envelope. As we increase those number of slits, especially if you contrast 2 and 7, we can see, okay, well, the fringe separation between the centres has stayed the same. That distance there is the same as that distance there. But those maxima have become clearer, they've become more defined. They also, so that means the bright bits get much, much brighter. The dark bits get darker. And so you essentially have a bigger contrast between the bright fringes and the dark fringes as we increase the number of slits. So we can see that down here, what's actually happening. If we take a little look, as we increase the number of slits, well, the height of that bright fringe intensity goes up. So we get a much, much brighter bright bit. And again, if we remember, intensity is proportional to amplitude squared. If we've got 4 slits with constructive superposition, so that means we'll have 4 times the amplitude when we've got constructive superposition. What does that mean for the intensity? So, again, if intensity is proportional to amplitude squared, well, that means my intensity will have gone up by a factor of 16. So you can see, well, 5 slits is going to go up by a factor of 25, and so on. One more question before I leave you. What would my single slit interference pattern look like if I used white light? So all of these things we've been looking at so far have been what we call monochromatic. So mono being one, chromatic being colour. So monochromatic means one colour or one frequency. So generally what we mean by that is a red laser or a blue laser. We can do the same single slit interference pattern with white light. So if I used a light bulb here, got my single slit, light going through, and if I've got a screen over here, I'm going to get this interference pattern. So, to give you guys a little clue, have a little think. Directly in front, how has the light been diffracted, if at all? And what does that mean for the colours of the spectrum? As you go further away, think about, okay, if we've got this equation, what happens as the wavelength changes? So if you think about your colours of your rainbow, which one has the longest wavelength? So as we increase that wavelength, what's going to happen to that angle there? Okay, so the answer looks like this. So if I take my picture here, so we can see, okay, on the top I've got monochromatic green light. So that's the interference pattern we are familiar with. Well, in reality, that central maxima would be much, much brighter than the next. So this is not terribly well drawn. Okay, but let's look at the other ones. So this is our white light single slit interference pattern. So here, well, this is a white central maxima. So why is that white? Well, white light is obviously all the colours of the rainbow mixed together. And so right in front, well, we haven't had any diffraction, so my red, my purple, my blue will all have been gone straight through, so we're going to have a white bit there. Then, let's take a little look. Well, we know that violet, indigo, they've got the shortest wavelength, so about 400 nanometers. So those are going to be, with the smallest value for lambda, they're going to have the smallest diffraction. So my violet light gets diffracted the least. Red, on the other hand, wavelength of about 700 nanometers, that's going to get diffracted the most. So we can see, as we get further and further out, those diffraction bands, the white light gets dispersed into the colours of the rainbow. And so you kind of get this smeared out rainbow effect occurring as you get further away. As we go further and further, we can see that that effect becomes even more pronounced to the point where those different rainbows will start blurring into each other and you can't make them out apart. So, I'm going to leave you... Watch back over this video again if there was anything that didn't make complete sense. What I'd like you guys to do now is to have a little go at the questions that I've attached onto the Firefly task and get those completed for next lesson.